Sometimes instead of being given all of the equilibrium concentrations and being asked to find K, sometimes you'll be given K and asked to work backwards and find the equilibrium concentrations. And here's a strategy that we use to do that. The problem-solving strategy that we use is often referred to as ICE tables. And you'll see how that acronym comes together in just a minute. So we'll write the balanced equation, write the equilibrium expression, list all the conditions, calculate Q so that we know what to expect, and define the changes. I'll show you how to do this using the coefficients from the balanced equation, apply the ICE table, and substitute the equilibrium concentration. Seems like a lot of steps. It won't be once we try to apply them. Let's try a sample problem. We have a 1 liter flask filled with 2 moles of, well, right away, I know that 2 moles out of 1 liter is a 2.00 molar concentration. And if I'm asked to work with anything, I'd rather have molarity. I just like to start with the right units. 3 molar after. All right. So we have the starting concentration of sulfur dioxide and nitrogen dioxide. After equilibrium, we have the final concentration or the equilibrium concentration of nitrogen monoxide. Calculate K. And step 1 is to write the balanced equation. That's actually already been done for us here, so I'm just going to write a little 1 to remind us that it's already been done. Let's check and make sure this equation is balanced, shall we? 1 sulfur, 1 nitrogen, 4 oxygens, 4. So that is a 1 to 1 to 1 to 1 mole ratio. And of course, this little box is just an arrow, and you can draw it both ways or one way. What's step 2? So step 2 is to write the equilibrium constant. I've got a little room here to write the expression. And remember, it's products over reactants. So let's fill in the products. The superscript is 1, so I don't need to write anything because the coefficient is 1, excuse me. Step 3 is to build an ICE table and fill in the information that I knew that I do have. So I'm going to build out an ICE table where I stands for initial concentration and C stands for change and E stands for equilibrium concentration. So ICE is an acronym for initial, change, and equilibrium concentrations. And I'll make this look a little bit more like a table. Sorry that I've got some writing in the background there. Hopefully we can overlook that. And let's start plugging in what I do know. I have the initial concentrations for sulfur dioxide. It was 2.00 molar for both. Do I know the initial concentrations of products? We can assume that that flask was empty if we weren't told otherwise. That means the initial concentration of products is 0. That will often be the case, but not always be the case. So if we're told we have some products in the beginning, then that's the information we have. But if we're not, then we can safely assume that most of the time it's 0. What about the change? Here's where we're going to use that rule where we kind of make some predictions based on the balanced equation. So the change in this case will be minus x. Why am I using a minus symbol? Because these are reactants, so I expect that they will be used up. Why am I using an x? Because I do not yet know the value. What about for nitrogen dioxide? Minus x again, because these are in a 1-to-1 ratio, so whenever x amount of the first thing is used up, x amount of the second thing I expect will be used as well. Plus x and plus x. Again, this time we're on the product side, so we're using a plus symbol to show that these things are being formed, and they're in the same ratio, right? If the balanced equation had a 2 in it, then I would put 2 in front of x because I would be using that ratio. Do I know any of the values for afterwards? Well, I was given at least 1, right? And remember that Q is products over react, but I know all the initial concentrations. So 0 and 0 are both of the products, and 2, I'm just using a shorthand, and 2 are both of the reactants. So really, it's just 0. If Q is 0, that's really small. We know that the equation will shift to the right. and we will expect it to make products. That's the only reason we do that, just to make that little prediction there. You might have been able to make that without doing that step, and I understand as you go forward, it's fine if you don't have to make that step. Clues to help us figure out what X is. Well, if we look at this column in the table, we see that sulfur trioxide starts out with a 0 molar concentration. X is added, and then at equilibrium, there's 1.3 molar. So we can kind of just read straight from the table that what was added must be 1.3. The X that was added is equal to the 1.3 molar. With that information, we can fill in the rest of the table. This must also be 1.3 molar. Now here we actually have 2 minus X. That's 2 minus 1.3. So be careful. Sometimes you're going to have to plug in X to determine what the value is. And here it's also 0.7 molar. So now I've got my table filled in, and what was I trying to find out? K. I can go back to my equilibrium expression for K, plug in the things from my table, and now we know the value. Setting up this table is a handy tool to help us sort of fill in the gaps for the information that we do not know from the information that we do know. So it's going to be 3.45. That is our equilibrium constant. Remember, there are no units. These numbers all had 3 significant figures, and this number was already in the middle of the page as well. So that's the new technique for solving problems that we'll be using. Let's do a couple of more of those. Here's another one. Let's draw in our arrow. A mixture of 0.5 moles of hydrogen and 0.5 moles of iodine was placed into a 1-liter stainless steel flask, so I can assume that flask was empty. Calculate the concentrations of all species at equilibrium. The value of K is given. So I'm going to again make an ice table. Let's start with my balanced equation. These are all gases. Remember, if I had a species that was a liquid or a solid, I would not include it in the equilibrium expression. I also do not need to include it in the ice table. I'm setting up my table knowing that I'll need it in a moment. Let's write my equilibrium expression. My equilibrium expression, K, is products. Well, let's go ahead and start plugging in what we do know. Initial concentrations for hydrogen. What about products? It's safe to assume there are no products unless we're told otherwise. How about the change? X amount will be used of hydrogen. That same amount should be used for iodine because these are in a 1-to-1 ratio in the balanced equation. Now, not only am I adding products, so I use a plus, not a minus, but also I'm adding the double amount. Why? Because the coefficient 2 in front lets me know that every time one reactant is used, 2 products are formed here. I don't have a given equilibrium concentration this time, so I've just written the algebraic expressions that represent them. I'm going to have to use these and plug them into the expression for K to solve for X, to isolate the variable X. So let's go ahead and do that. I've already written my expression for K up here, so I'm just going to copy it, paste it down here, and then start plugging in the things that I do know. We know the value for K. And we can start to simplify this equation. So we've done a little work to find the value for x, but what were we trying to solve for? So we're going to need to do a little bit more solving and plugging things in. The value of x is 0.393. So if we use that, let's change colors here. 2 times 0.393 would give us the value for the product. And for the previous scenarios, zero point 0.5 minus 0.393 would give us the values for the reactants, which happens to be 0.107, already written here. So now we know the concentrations. Remember, we can still do this using pressure. Things are the same, the equation is the same, and here's a sample problem. At a certain temperature, the equilibrium constant found using pressure is given for the following reactions. Oh, be careful. We actually have a solid this time, which means it will not be written in the equilibrium expression. In an experiment carried out, a certain amount of reactant is placed in a evacuated container, so that means there was no product in there, and allowed to come to equilibrium. Calculate the total pressure in the container at equilibrium. Well, if you recall, total pressure is the sum of all the partial pressures. So if we can figure out the partial pressure of each of these and add them together, that will be the total pressure. We're going to use the same ice table method. Let me add an extra page so that I'm not running out of room. Feel free to add a page to your notes as well, so you've got a little bit of extra writing room. And we'll start with our balanced equation. We'll write our equilibrium expression. And remember, solids are not included, so there'll be nothing in the denominator here. That's our equilibrium expression. Then we'll build our ice table. And plug in the information that we do have. We know that initially there were no products because it said the container was evacuated. We know that plus 2x is the value of ammonia that will be produced, and for every plus 2x, there'll be x plus x of carbon dioxide produced. So this is 2x and x. Now, we have the value for Kp. It was 2.9 times 10 to the negative 3. Let's plug that in. And that's actually going to be equal to 2x and x. So that's going to be 4x squared times 1x, x squared times 1x, which is 4x cubed, divided by 4. And then we need to take the cubed root of this number. So the cubed root, I think, is in the math portion of your calculator. You push the math button and then find the cube root, which is item number 4, and go ahead and put the number in, and we get that cubed root. So x is actually 0.089. Now be careful, again, I don't think we were just solving for x. We have the 2x value. We were asked to find P total. So P total is the pressure of the ammonia plus the pressure of the carbon dioxide. So we'll have to add these numbers together. And with two significant figures, it looks like. So these are what we're going to try for homework.